Regression is probably the most useful thing you will learn in this course. In particular, we're going to spend a lot of time looking at simple linear regression, but you'll see that it extends quite naturally to more complex regressions. Um, Simple linear regression is kind of the crowning achievement of statistics, I think, because it incorporates a lot of the techniques that we've seen in other places. So, for example, um, we're going to be looking at sources of variance, which we saw when we were dealing with an ANOVA. It also deals with this, we're interested in idea of correlations of variables, and of course, going along with that is a covariance also. You'll see that we also have within this technique hypothesis tests. In particular, we're going to see we're going to have an F-test in there, and we're going to have potentially several t-tests. And of course, going along with hypothesis tests is probability distributions, because in a hypothesis test you are producing a null hypothesis that assumes some kind of probability distribution for the random variable. Okay, so you see this is an extremely rich method, and you'll see that this is used quite a bit in business, particularly in the area of forecasting, which we'll take a look at in a few days. Okay, all right. So what is it that we're actually trying to do with regression? Okay, there are lots of times when we're interested in looking at the relationship between two variables. So just to give a really rough example here, like let's say we have we've often had observations that were like this. So we have person A, B, and C, and then let's say we have, for each person, we have a measurement of height and a measurement of weight. Okay, so we have, for each person, we've got a height and a weight. And we might ask, is there a relationship between these two? Okay, now, something, a more practical business kind of application would be something like, let's say we have company A, B, and C, and we have number of employees. So that's one measure of size, is number of employees. There are a bunch of different measures of company size, and we could say percentage of turnover. So we might ask, and that's very sloppy, but that says turnover. We might ask, well, okay, so each company has a number of employees and a percentage of turnover, and we might want to know, is there a relationship here where we might be able to predict based on size what a normal turnover would be, and to see if we have an unusually large amount of turnover. Or, I don't know that there is a relationship. I suspect that this has been investigated somewhere, but so the basic idea is that we have a relationship between two variables, okay? And a lot of times, they're random variables, so their value is determined somewhat randomly. But also, there's a random component and a predictable component, and we often call one y and one x. Okay, so some other examples of where we might be interested in the relationship between two variables. Can you predict the rent on an apartment given its distance from campus? Okay, I suspect that there are several factors that go into the rent. Number of bedrooms, the light versus dark side, or the newness, the quality of the fixtures, and so forth. But if we want to just compare, we want to look at the relationship between the rent and distance. We might this we'll call rent our y, and we're going to try to predict rent, and the distance would be x. Okay. Can you predict your score on an exam given the number of hours you've studied? Okay, so we can say, okay, well, in this case, we're trying to predict the score. So that's our y based on the number of hours. And so the hours of study would be our x. Okay, so we're going to try to predict y based on x. Can you predict a delivery tip given the median home price? And this example comes from one of my previous students who felt quite sure that there was a very strong positive relationship between the tip that you can expect and the median home price of the neighborhood that you are delivering to. He also said that there was a strong relationship between whether the person who answered the door was male or female. But we'll look at binary variables 2 lessons from now. So, we've looked at relationships between, okay, well, I might as well just for completeness mark this. So, the amount of tip would be our y and the price would be our x. Okay, so we're trying to predict y given x. Now, we have looked at relationships between 2 variables before, and we had 2 ways of doing it. Of course, we had the covariance and we had the correlation coefficient. These were our 2, the 2 tools that we had for understanding the relationship between 2 random variables. But there are limitations to what covariance and correlation will tell you. For example, if we do have, I'm going to write this just so that you'll know that this is a correlation. Let's say you do have a correlation coefficient of 0.72 between, let's say, pizza delivery tip and price. This tells you that there's a strong positive relationship, but it doesn't actually allow you to predict anything. It doesn't actually say, okay, well, if the median home value rises by $8,000, what can we expect to have happen with the tip? So correlation and covariance don't allow us to predict. Okay. Another weakness of the covariance and correlation is that it also doesn't allow us to control. Okay. There may be some kind of relationship, but we don't know if there might be other factors that once you control for those, how strong is the relationship? Okay, so the ability to predict y from x and the ability to control for other variables is what we get when we do regression. Okay, so regression allows you to do a lot more with understanding the relationship between these 2 variables. Okay, so let's start off with an example, and this is an example that's in the lecture slides, but I have copied this house price data onto into this Excel worksheet here, and I'm gonna zoom a little bit in so we can look at it. Okay, so what we are interested in is there a relationship between the number of square feet, that is the size of the floor plan of the house, and the house price? Okay, so we want to explore this relationship. Okay, now we suspect that square feet has some impact on price. Okay, we know that there's other things, but we're interested specifically in how does the size affect the house price. So we're going to call this square feet our x, right? Because this will be our independent variable. So this one will be the variable that is that's first. Okay, the builder decides on a square feet, and then this has some kind of effect on the dependent variable. So we're going to call the house price the dependent variable. Now we have to be careful about what we're saying theoretically. Regression does not assume a cause. Okay, does not assume or prove a cause. Okay, we're not able to say that square feet is the cause of a house price. All we're interested in saying is whether there is a relationship, if there is an effect. Okay, but that's kind of the inverse of cause. I don't mean to say that. We just want to see if there is some kind of a relationship between these two. Okay, and that's as specific as we can get. In order to prove a cause, you have to have very tightly controlled experimental conditions and random assignment to conditions and manipulation and so forth. But so we can't do that just by analyzing existing data. So let's go ahead and start in a good place. If we're trying to understand these, a scatter plot should be our first stop. So we'll do that. I'll just go ahead and select these variables. Actually, let me just select them. Actually, I want to do this. And on the Insert tab over here under Charts, you'll see a scatter, and we'll just select that one at first. Okay. Now, we've designated that the square feet is our independent variable, right? But it looks like, based on what we have here, that Excel put the house price on the x-axis and put the square feet on the y-axis. So we have to kind of flip this over. I'm going to show you a way around this later, but I'll go ahead and show you this. If you come to select data, I find it easiest to just remove the data series that they've added, because then when you click there, you can select what is going to be your x. So we say these will be our x values. Okay, and actually let me just select the values themselves. So the square feet will be our x, and our y will be the price. Okay, and then when I hit OK, okay, so now it's transposed now so that we have square feet here and house price here. Okay, so this is our independent and our dependent. Now, what can we conclude about this scatter plot? Well, for one thing, it does appear that there is a positive relationship. That is, as the square feet goes up, the house price appears to go up. And note that these are in thousands of dollars. Okay, we can also see that it's a fairly strong relationship, because as remember the diagrams that we saw when we were talking about correlations. The tighter these things sit around a line, the stronger the relationship. So I'm going to just, if you click on the data points and right click and then go to add a trend line. Okay, so we can see visually, if we draw a line here, that this line does a pretty good job of summarizing this relationship. Okay, we can see that it's not perfect. There are, most of the points don't actually fall on the line, but this line is a pretty good approximation of how these two variables are related. Now, as you know, a line has an equation. Okay, so you might notice down here on the right, once you've added a trend line, you have the option of displaying the equation for that line on the chart. Okay, so I'm just going to do that, display that equation. Okay. Okay, so this is all that we are doing when we're doing regression. All we're doing is coming up with a line that describes the relationship between the two variables. And then you'll see later, once we have that line, all we have to do is plug our independent variable into this, and we can predict our y, which is what we wanted to do. That was our goal, to predict. Okay. So let me just review just a a little bit of high school algebra, remember that the equation of a line was just y is equal to mx plus b. So this is the slope-intercept form of the equation of a line. And so this means that this is our independent variable, and this is our dependent variable, and this was our slope, and this was our intercept. Okay, so on our axes then, we've got x here and y here, and if we look at this line, then this point right here, where the line hits the y-axis, is our intercept, so that's going to be that b right there. And the slope of this line, okay, so that is the change in y over change in x, delta y over delta x. So it's the slope of this line, and that's that m right there. So for example, we can see, if this is, we'll put tick marks here. This is 1 and 2, and this is 1 and 2. The equation for this line, okay, it's hitting the y-intercept at 1, so it's going to be y is equal to 1. Well, let's put the slope first. So the slope appears to be, it goes up 1 for every time it goes over 1. So the slope is 1 too. So this will be y is equal to 1x plus 1. Okay, so very simple review there. I'm going to, as a way of introducing, the regression notation, is to just rearrange this equation a little bit, and we'll put the intercept first. Okay, and I'm also going to add to this. We used uppercase letters to represent our random variables, so we'll do that too. And okay, so we'll just do it one step at a time. So m times uppercase x. Okay, and we can change this again by taking into consideration the notation. Instead of just using lowercase b, we're trying to make a claim here about a population. And remember that population parameters were often designated with Greek letters. So I'm going to change this to beta, and I'm going to call this one beta naught plus, and now this slope here is also a population parameter. So I'm going to change that also to beta, but I'm going to call that beta 1 and put in my x. Now, we have to acknowledge that we understand that a line will never perfectly describe a population. So we're going to roll into this equation an idea that we know there's going to be some error. Okay, then this error is going to be the difference between what we observe and what the true value is. So we're going to say in our model here, we'll call this our model, we're going to put in an epsilon. That's the Greek letter epsilon, and that's going to be the amount of error. Okay, so we've got this is really still just an equation for a line. This error is just changing the intercept a little bit, but it's still an equation for a line. And remember that we're going to be going line by line here, right? Because we're going to have, so for example, with company A, number of employees, they had a number of employees and they had a percentage turnover. So we're going to say that let's do a subscript of I, which is row I. Okay, so the y variable in row I is going to be some intercept, and this intercept applies to all rows, so we're not going to subscript it, plus, and this is also universal, doesn't apply to just the line. So we do have to say that this is the x for that row plus the error for that row. Okay, so now what you'll see on the next slide is that this is the model for regression. But I wanted you to see that this is nothing more than a line that we have, the equation for a line that we have rewritten to incorporate the fact that these are population parameters, that there's going to be some error, and that each of these y's and x's have to be on the same corresponding row. Okay, so let's take a look then at what that model does look like then. Okay, all right, so here it is, and this is how it appears in your book and on your and on the other slides. So this is exactly what we had before. See, there's our line subscript. This is our population y-intercept, and this is our slope. So remember that this was b in our original line equation, and this was m, and there's x, and there's that error. Okay, so just remember that this is linear regression, which means all we're doing is coming up with a line that describes the relationship between two variables, specifically this independent x and this dependent y. Okay, now so this is our population model. Okay, so notice that this is the claim that we are making, is that these apply to the whole population. Okay, but if we're coming up with this line, we're doing it on the basis of having drawn a sample, right? So remember that when we had the Greek letter for the average and we estimated it from a sample, it became x bar, and when we had sigma, it became s. Okay, so likewise, we have to take these population parameters and then say, okay, well, we're really just estimating these on the basis of a sample. So we're going to rewrite this again as what you see on the next slide. Okay, actually, let me go to the next one. Okay. Okay, so now let me go through what this one is saying. So this is a slight modification of that original population model, only now, so we still have the y sub I and the x sub I, only now a couple of things have changed. We put this little circumflex over here, this little, sometimes called a hat. We put this little hat on the y to indicate that this is just an estimate. This is an estimate based on a sample, okay? So what we're actually going to be coming up with is an estimate for what the dependent variable will be based on our sample, okay? So instead of using beta now, we've gone to lowercase b, and we still use this, the subscript naught here, or 0, and subscript 0. So this again is the slope, and this again is the x variable for that row. Okay, so this is actually what we're going to be coming up with. So this is our theory. This is our theoretical idea of what we're doing by describing the relationship between these two population variables. And this is what we're actually going to come up with. So it all comes down to, we need to have an estimate of the intercept and an estimate of the slope. And then once we have those two things, then we can do our prediction. Okay? But by writing it this way, we are acknowledging that this is just an estimate. Okay? Okay. All right, so let's go ahead and let's define one more thing before we do an example. Okay. Now, in order to come up with beta naught and beta 1, as we said, these are estimates. We have to have something that's called an estimating method. Okay. So how do we get these two? How do we obtain them? So we have an estimation method. And the particular one that we're going to be using is called ordinary least squares, or OLS for short. And the reason why it's called ordinary is just that it was really the most intuitively obvious and the most basic and the one that's been around forever. So it's called ordinary to differentiate it from other estimation methods like generalized least squares or weighted least squares, or there are any number of them, maximum likelihood plus a bunch named after, two statisticians. But we're really, we're just going to stick with ordinary least squares. And thankfully, this is what Excel uses. Okay. So Excel uses ordinary least squares. And so it really comes down to this. What we're doing is we're trying to come up with a beta naught and a beta 1 such that we are minimizing how far off we are. Okay, so let's take a look back here. So when we draw a line, we are going to be off by a certain amount. Okay, invariably, most of these are not going to be precisely on the line. So what we want to do is draw the line such that these distances are minimized, right? And so here these are called errors. These are actually residuals, but the difference between these two, remember, so this red thing here is the line that we've drawn, and this distance between the line and the actual value that we observed is actually, it's not called the error, it's actually called the residual. And so this is going to be the real y sub I minus, and then this value is what we predicted, so minus y hat sub I. So that's what our residual is. So what we're trying to do is to minimize our residuals. So, or we could just say minimize the sum of those, but then if we just do that, we're going to have to deal with positives and negatives. So we minimize the sums of the squared residuals. Okay. Now, I'm not going to actually ask you to do that, but your homework assignment does tell you, find the ordinary least squares estimates for this data, and you should just know that this is the most basic way to do it, and this is the way that Excel does it. Okay, so that's what it's called. So we're minimizing the sum of the squared residuals. Okay, and the reason why this substitutes this expression here is this is actually, remember that we had y hat sub I was equal to beta naught plus beta 1 x sub I. So it just substituted this in for this. So that's all that changed there. But the basic idea is that the closer we want to draw a line such that those distances are as small as possible. Okay, well, let's go ahead and do that then. Let's see how we do that with our housing first, and then I'm going to do an example from the homework afterward. So we did this using just adding a trend line. And okay, all right. So we did this just with by right-clicking and adding a trend line. But let's go ahead and use the data analysis tool pack to actually do the official regression, because we'll see that that gives us a lot more output that we can use later for, say, assessing the model fit, which we're going to do next time. Okay, so I want to regress house price on square feet. So by convention, you are regressing your y variable on your x variable. So let's do that. data analysis, and regression is right here under rank and percentile, regression. Okay, so now you just select your Y range, and I'm going to go ahead and keep the labels because that will help me with the output. I just have to make sure that I click there for labels. Input X, so that's going to be this square foot column here. Okay, and let's go ahead and put the output in a new worksheet so that will have more room. Okay, and then I just click OK. All right, and there it is. Now, there's a lot on here. I'm going to show you that we're only going to use a little bit of this today. Once again, I'm going to round these numbers to 3 decimal places just to make it easier to read. Okay, so there's a lot on here, and you're going to learn your way around this sheet pretty well. But for our purposes right now, we're going to concentrate on this little area right here. Okay, so it gives us these estimates now. So what this is telling us is that our intercept, or our beta naught, is 98.248, and our slope, so this is the coefficient on the square feet variable, so this is x, so this is the slope, so that's beta 1 is 0.110. Okay, so this is it. I mean, this is our predictive model. This is all we need, and so if we were to write the equation of this line, all we would have to do is say that y, or y hat, is equal to this. Okay, so y is equal to 98.248 plus 0.11 times x, okay, whatever that x in that row is. Okay, so if we go back here and look at when we just drew the line, we see that that's 98.248 and then 0.109. I think maybe I had maybe if I added more decimal places here, it would round it slightly differently. Probably be closer, closer to what we saw on the other sheet. So it is the same. 0.1098, is that what it had? Yeah, 0.1098, 98248. Yeah, okay, so now they match. So the equation for this line, well, is the same one that just appeared on the sheet before, 1098. Okay, so now all I have to do is plug my x in for that, and I can predict any value that I've never seen before. Okay, now so there's one more thing I want to emphasize before I go on to an example from the homework, and that is how exactly you interpret these. So we have our equation now. We can, we have our line. We can do our prediction. But if I were to ask you, well, how do we predict? How do we interpret what these numbers mean? Okay, so it's given to you on this slide. So beta 0 is the estimated average value of y when the value of x is 0. Now this doesn't always make sense, but like let's say for example here, our y-intercept, our beta naught right here, was 98. Okay, now remember that this is in thousands, so that would tell us that when x is 0, that is when square feet is 0, the cost of the house is $98,000. Okay, so this doesn't really make any sense here, but the idea is, the principle is that based on this equation, as and you can just see, let's see, can I zoom in a little bit more here? Based on this equation, if you plug in 0 for x, then you will wind up with 98,000. Okay, so this is an example of a case where that intercept, while that does appear to be the true value of that estimate when x is 0, that doesn't really make much sense in the real world because you can't have a size 0 house. Okay. Okay, so that's the interpretation of the intercept. And what about the slope? So the correct understanding of what this slope variable means is, so this beta 1 here, it's the estimated change in the average value of y as a result of a 1 unit increase in x. Okay, so that's really just the definition of slope, right? So as x goes up 1, this beta 1 describes its effect on y. Okay, so in our example, for every additional 1 square foot, this beta 1 is the change in price in thousands. So let's take a look at that. Okay, so this is our beta 1. So interpretation is, okay, for a one square foot increase in size, we can expect a 0.1098 wound up being the rounded version, right? 0.1098 increase in price in thousands, right? Okay, so for a 1 square foot increase in size, we can expect a 0.1098 increase in price in thousands. Okay, so 10% increase in price. Okay, what is a sorry 10 what is 0.11 of 1,000? Okay, so that's 110. So really the way to interpret this is for a 1 square foot increase in size, there's an increase of $110 in the price of the house. Okay, so just know that that's how you read these. So for a 1 unit increase in x, this is the size of the unit change in y. Now, if this had been negative, that would mean that there's an inverse relationship here. So as square feet goes up, price goes down. That probably wouldn't be the case here, but because of the sign of this coefficient, that tells us the direction of the relationship. Okay. All right. So I want to finish off by doing an example in the homework. Okay. Let me log back in just to make sure that I can submit answers here. So MSL 11 preview. Okay, and so one of these questions asks you this. Okay, a coffee company uses a data-based approach to improving the quality and customer satisfaction of its products. When survey data indicated that the coffee company needed to improve its package sealing process, an experiment was conducted to determine the factors in the bag sealing equipment that might be affecting the ease of opening the bag without tearing the inner liner of the bag. One factor that could affect the rating of the ability of the bag to resist tears was the plate gap on the bag sealing equipment. Data were collected on 19 bags. Okay, so just to back up a little bit, so just to understand the context of the problem a little bit better. So the idea is that we have this company that makes these bags of coffee, and the bags have to really be airtight, maybe with a little valve to let some air escape in order to preserve the coffee, because coffee taste starts deteriorating as soon as you grind it. Okay, so they need to have airtight. And when the customer opens the bag and they tear the bag, that interferes with the quality, because over time the coffee is going to taste worse and worse. So they want to determine, well, okay, what factors of our actually sealing the bag, what factors of the process actually affect how likely they are to tear these things. So they came up with some kind of metric of tearability. So they have they came up with some kind of measure of how terrible, TEAR, so terrible the liner is. Okay, the plastic liner inside this foil packaging. So how terrible it is, it's some kind of metric. Okay, so that's one thing. So that's we want to know what the effect of, we want to predict the tearability. Okay, so this will be our y. Okay, and the x variable then has to do with this machine that they use to seal these. So the one, the variable that they wanted to investigate, what is this variable's effect on the tearability, is some kind of plate gap. So I assume that 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 this that this is the gap that they're talking about, but the idea is that they have a gap here of a certain size. So the gap on their sealing equipment, and its effect on how rippable these bag liners are. Okay, so that means that the plate gap is the x variable. Okay, so I just put these here because the problem is very abstract when it's just on the page, and it's hard to really understand what's going on here. But basically they just want to see, well, are there some adjustments that we can make to how we seal these things, that will make it less likely for them to tear these things. Okay, so let's go ahead and answer the question then. So we come here. Okay, so complete parts A through E, so it's a fairly long question. And I'll click here to get the data. So there's that tear rating, or tearability as I called it, and the plate gap. So again, plate gap is our X and tear rating is our Y. I want to put these on the clipboard and then copy them, and I'll go into Excel and start a new sheet. Okay. All right, and there they are. So the first thing you should always do when you're going to do regression, then, which the first question actually gives you this clue, you construct a scatter plot. So we want to do a scatter plot. Now remember last time when we made a scatter plot, the order of the variables was reversed, just because of the default behavior of Excel. It turns out that if I just move this over here, my default scatter plot will be the way I want it. So go to Insert and Scatter Plot. Okay, now this should give you some surprise, because this isn't nearly as obviously a linear relationship as we had before. So we see things are quite bizarre. It appears to be somewhat of a positive relationship, but if we were to draw a line here, add the trend line, this is, it looks like it's kind of negatively sloped. But this, we'll see later that, a model like this probably wouldn't be very useful in practice. But for now, we'll just go ahead and say, okay, well, this is how it looks, and this is what we have. So let's go back to the question. Okay, so choose the correct plot. So if I look back here, it looks like we had, mostly negative values, a lot of clustering down here, a couple of outliers up here. It looks like this one, C. Now everyone's going to look different. Mine happens to look like this, so okay. Now, assuming a linear relationship, use the least squares method to find the regression coefficients. Okay, so all this means is to just do the regression and find beta naught and beta 1. So we can do that by right-clicking, but let's go ahead and do the regression the official way. So data analysis, regression. Okay, so my y now is the tear rating, so that's my dependent variable. X variable is the plate gap. And notice that that can be negative. Okay, I'm going to keep the labels on there. I think I'll put this actually on here so that I can look at it. Okay, and all right. Okay, let me check what I did wrong here. Okay, looks like my y didn't select correctly. So this was my y. Okay, x b2 to be, yeah, that's right. Okay. All right, summary output there is okay. All right, move this over a little bit. Okay, so again, this is what we're interested in. Okay, so this is our intercept, and that's our slope. And so we can put these in round to 4 decimal places. We'll have Excel do it. So number and 4. Okay, so 0.7591, 0.7591, and beta 1 negative 0.2909. Negative 0.2909. Hope I did that right. Okay. Okay, so now interpret the meaning of the slope in this problem. Okay, now notice that we have a negative slope, which we observed on our scatter plot. So now what's happening is as the plate gap gets bigger, the tear rating will go down. Okay, so they move in opposite directions. So that would mean that the interpretation of the slope is for a 1 unit increase in the gap, we would expect a 0.2909 decrease in the tear rating. Okay, so let's see what we have here. For a 1 unit increase, the tear rating is expected to increase by beta 1. For the approximate plate gap, these two are just wrong. For each increase of 1 in the tear rating, the plate gap is expected to increase by beta 1 units. Okay, so this reverses the dependent and independent variable. Okay, and these just are not right at all. But let's look at this one. For each 1 unit increase in the plate gap, the tear rating is expected to increase by beta 1. Yes, it increases by a negative number, so it's a little bit backwards, but in the phrasing, but we'll take that one. Okay. All right, so predict the mean tear rating when the plate gap is equal to 0. Okay, so what's this asking? This is just the intercept, right? So when the plate gap is 0, so when x is 0, y is just equal to the intercept. So we'll take the intercept, which is 0.7591. Okay. And so what should you tell management of the coffee company about the relationship between plate gap and tear rating? Now, this one is a little bit tricky because as we'll see when we get into evaluating model fit next time, there are many reasons why we should conclude that there's not really any relationship at all between these two. But for the purposes of this assignment, let's just pretend that the model is fine and that there's this relationship and that these estimates describe that relationship. So what should you tell management? As the tear rating increases, the plate gap decreases. The plate gap is affected by the tear rating. Well, that's reversing the dependent and independent again. The tear rating is affected by the plate gap. As the plate gap increases, the tear rating decreases. Okay, that's a candidate one. Let's read all of them. As the plate gap increases, the tear rating increases. No, that's not. It doesn't increase. And the tear rating is not affected by the plate gap. Now, as I said, D is probably the actual right answer, but for now, we'll just assume B. Okay. Okay, so hopefully that helps. Um, uh, uh, as we, as I said, there's a lot more to do with regression because this is the simple linear case where we're just fitting a line and we've got our parameters. Next time we're going to be looking at how well does that line fit, and then we're also going to look at, well, we can fit other shapes, and so we can make predictive models that are more sophisticated than lines and be more accurate with our predictions.